everyone. I welcome you all in lecture 6 of this course, Mechanics of Solids. And what we have discussed in last lecture was regarding concept of shear stress. What we understand by shear stress is the two equal and opposite forces, internal forces, are trying to cut a particular segment. That is shear stress. And the discussion regarding this was discussed in the last lecture, and the additional example was given to you, like on these two plates which are connected with the board, if tensile forces are acting, and due to these two tensile forces, that plates will be trying to move in that particular direction in which that force is applied, then that particular bolt may cut at this particular position, and it may fail in this particular manner. So that kind of failure is called as shear failure. And in addition to this, what we have discussed was about complementary shear stress, concept of that. And what we have discussed is, now in addition to these two equal and opposite shear stresses, these two shear stresses trying to create a couple in clockwise direction, and for equilibrium we need some anti-clockwise couple so that that particular segment will be in equilibrium, and this additional internal stress is called as complementary shear stress. So this part we have discussed in last lecture. So also we have discussed about shear strain, and in that discussion what was discussed is, due to these shear stresses, what will happen, that the one of these diagonals will be getting to elongation, and in the another diagonal it will be subjected to compression. And so due to elongation and compression of different diagonals, the angle will be getting changed, and with horizontal if it is phi by 2, and with vertical if it is phi by 2, that together phi is called as shear strain, and units for shear strain are radians. So this discussion we have done in last lecture. In addition to that, like Young's modulus, the constant between shear stress and shear strain within elastic limit is called the modulus of rigidity or shear modulus, and we denote it by capital G. So that capital G is equal to tau divided by phi, where tau is that shear stress and phi is shear strain. So this much discussion we have done in last lecture. So today we will go for further discussion regarding different stress systems which we analyze in different cases. So earlier what we have discussed regarding either tensile stress or compressive stress, that discussion or those numerical were related to one-dimensional stress analysis. So what we have done in one-dimensional stress analysis is, what we understand by one-dimensional is, force is acting along one axis, and due to that force, what is happening with that particular material or with that particular member, that we have analyzed. So stress we have said as P divided by A, if P is the force applied and A is area of cross section, and longitudinal strain in that particular direction in which the force is applied, we have said as longitudinal strain, epsilon is equal to delta L by L. So delta L is change in length, and L is original length. So with this we said that within elastic limit, stress is directly proportional to strain, and that was Hooke's law, and the constant of proportionality is Young's modulus or modulus of elasticity. So that we have discussed up till now. So change in dimension in lateral direction. So what will be happening, due to force applied in a particular direction, the other dimension or dimension in other direction will be getting elongated or compressed. So that is called as lateral strain, and we have discussed that lateral strain to longitudinal strain is constant, and that constant is called as Poisson's ratio. So lateral strain is minus mu times epsilon, or if epsilon is equal to sigma divided by capital E, then lateral strain is minus mu times sigma divided by E. So with this, what we have discussed is something like this. So if the force is applied over here as a tensile force and it is along this axis, okay, then along this longitudinal force, due to this longitudinal force, there will be elongation of the length, elongation in this particular direction. And due to this, if this is the cross section on which this force is applied, that cross section will be getting compressed. So that is what is lateral strain. So if it is a two-dimensional stress system, what will happen to it? Try to understand. Okay. So due to say sigma x, now over here in this particular one-dimensional stress system, we have applied force over here P, and that P divided by A is sigma. So if this is x-axis, then what we can say is this is sigma x in this particular direction. Okay. So about x-axis, if it is sigma x, and about y-axis, again there is some force acting on this axis, and on this particular area of cross section there will be some stress sigma, and if this is y-axis, let us call it as sigma y. Okay. So what will happen due to this? Now only if sigma x is there, only if this force is acting, then what we have discussed earlier is this thing. Okay. So due to sigma x, along the x-axis there will be elongation, so that is epsilon x. But due to sigma x, along y-axis there will be a lateral strain, and that is epsilon y. Due to lateral means due to sigma x, what is happening along y-axis. So if I am considering sigma x force only, due to sigma x there will be elongation along x-axis, and there will be compression along y-axis. So that strain is lateral strain. And suppose if only sigma y is acting, then what will happen to it? Now if only sigma y is there, then there will be elongation along y-axis and compression along x-axis. So if only sigma y is acting over there, then longitudinal strain will be along y-axis and lateral strain will be along x-axis. Now what will happen if sigma x and sigma y both are acting together? Then we need to consider one of the stress as direct stress or along the longitudinal direction, and due to another stress or force, there will be lateral strain taking place. So how we can write for this together is, now try to understand. What we have written in first diagram was epsilon x is equal to sigma x divided by E. So due to this sigma x, the strain in x direction will be sigma x divided by E. But due to sigma y along x-axis there will be compression. So that is mu times, that is Poisson's ratio. So minus mu times sigma y divided by E. So due to sigma y there will be some compression in x direction. Similarly, when we are considering y-axis, so strain along y-axis will be due to sigma y, and that is longitudinal for y-axis. So epsilon y will be equal to sigma y divided by E, and due to sigma x there will be lateral strain along y-axis. So that will become minus mu times sigma x divided by E. So this total together will be the strain along x-axis and along y-axis. So now this is the system which is called as two-dimensional stress system. So what happens with this is these kind of equations. So for two-dimensional stress system, epsilon x will become sigma x divided by E minus mu times sigma y divided by E. So what is meaning of this? Due to sigma x there will be elongation along x-axis, and due to sigma y there will be compression along x-axis. Okay, and what will happen to y? Epsilon y will be equal to sigma y divided by E. So due to sigma y there will be elongation along y-axis, and due to sigma x there will be compression along y-axis. So it gives us in a two-dimensional stress system, strain in x direction will be due to sigma x as well as due to sigma y. So one is direct, another is the lateral, or one is longitudinal, another is due to lateral. Similarly, epsilon y, this part sigma y divided by E is longitudinal, and minus mu times sigma x divided by E, this is lateral. Okay, so with this we'll go further with one more system as a three-dimensional stress system. Now what is shown in this particular diagram is these three axes, x-axis, y-axis and z-axis together. If the stress system is in the three axes, so all sigma x, sigma y, sigma z are acting together. So what will happen to it? Now in addition to this sigma y, due to sigma z there will be compression, or there will be some lateral strain along x-axis. So epsilon x will become sigma x divided by E minus, due to sigma y there will be lateral along x-axis, and due to sigma z there will be lateral along x-axis. So there will be minus mu times sigma y divided by E and minus mu times sigma z divided by E. Again, if we consider y-axis, what will be strain about y-axis is epsilon y. Now due to sigma y there will be the longitudinal, and that will be this part sigma y divided by E, and due to sigma x and sigma z along y-axis there will be lateral strain. So that will become minus mu times sigma x divided by E and minus mu times sigma z divided by E. Similarly, for z-axis, strain will become minus mu times sigma x divided by E minus mu times sigma y divided by E plus sigma z divided by E. So if we are considering this axis, z axis, due to sigma z there will be longitudinal, okay, and due to sigma y and sigma x there will be lateral. So like this the equations will be for a three-dimensional stress system. So further what we will discuss is about what will be change in volume. Like in case of strain, we said that it is a ratio of change in length to original length, or change in dimension to the original dimension. So if we are analyzing three-dimensional stress system, then there will be change in volume. So we will discuss about volumetric strain. Say for example, along x-axis, y-y and z-z axis we have sigma x, sigma y and sigma z stresses, and it is given in this diagram that all these stresses are tensile. And let us say along x-axis the dimension of that cube is A, along y-axis that dimension is b, small b, and along z-axis that dimension is c. So with these dimensions, what can be written as volumetric strain is defined as the ratio of increase in volume of a body to its original volume when it is acted upon by three mutually perpendicular stresses. So what we have dimensions A, B and C along x, y and z axis of that particular cube. Then initial volume is A into B into C. And final volume, what we have, if epsilon x is strain, total strain in x direction due to all sigma x, sigma y and sigma z, then the change in length will be A into epsilon x, and change in dimension along the y axis will be B into epsilon y, and similarly change in dimension about z axis will be C into epsilon z. So final volume or final dimension will become A plus A into epsilon x. Similarly along y axis it will become B plus B into epsilon y, and along z axis it will become C plus C into epsilon z. Okay, so what further can be written is, now from this complete part A, B and C, this is taken out, and what is written over here is this becomes 1, and over here this remaining is epsilon x. So what it will give, A into B into C in bracket 1 plus epsilon x, 1 plus epsilon y, and 1 plus epsilon z. So with this, what we can write? Volumetric strain. So what it will be? It will be ratio of change in volume to original volume. So the final volume is this equation, A, B, C multiplied by these brackets 1 plus epsilon x, 1 plus epsilon y, and 1 plus epsilon z. So this is final volume minus initial volume. Initial volume was A, B, C. So this part. So this minus this will give you final volume minus initial volume will give you change in volume. And change in volume divided by original volume will give you volumetric strain. So what we can write further is this A into B into C, this part, if we cancel it, and over here that will become 1. So this is minus 1, and these three parts as it is. So this gives us volumetric strain. So if we simplify it further, what it will give us is this complete part. And now try to understand that strain is very small value, and this multiplication of epsilon x and epsilon y, or epsilon y and epsilon z, and epsilon x and epsilon z, so these three terms will be very small, and this can be neglected. So this 1 and this minus 1, it gives 0, and these are neglected, these three terms, and the remaining three terms, epsilon x plus epsilon y plus epsilon z, these are considered for further analysis. So what we write is volumetric strain is equal to change in volume to original volume. Delta V divided by V is epsilon V is equal to epsilon x plus epsilon y plus epsilon z. So this relation gives us what is volumetric strain when three mutually perpendicular stresses are acting on in three different directions. So with this, what we can discuss is volumetric strain is equal to delta V by V is equal to epsilon x plus epsilon y plus epsilon z. So we will go further. If we analyze it by those equations which we have already written for three-dimensional stress analysis, was this part. So in terms of stresses, if epsilon x is given as sigma x divided by capital E minus mu times sigma y divided by capital E minus mu times sigma z divided by capital E. So if those three parts are written for epsilon x as well as for epsilon y and for epsilon z, so if we consider these three terms in terms of stresses, then further that can be written as this sigma x over here, and again minus mu times sigma x divided by E over here, again in epsilon z we have minus mu times sigma x divided by E. So sigma x divided by E, if we take common, so what is remaining in this part, epsilon x, the remaining thing is 1. Over here it is minus mu, and over here it is minus mu. So these two terms together becomes minus 2 times mu. Similarly, over here from this epsilon y part, if we consider this sigma y by E, and if we consider from epsilon x minus mu times sigma y by E, and from epsilon z minus mu times sigma y divided by E. So if we take sigma y divided by E common, so remaining will be 1 from this part and minus mu from this part, minus mu from this part. So this will give you 1, again 1 plus 2 mu. Sorry, 1 minus 2 mu. So what is done from all these three parts is sigma x, sigma y, sigma z is taken common outside, sigma x plus sigma y plus sigma z, and over here in each part capital E is there, so it is taken out, and remaining term becomes 1 minus 2 mu for each sigma x, sigma y and sigma z. So this complete equation can be written as delta V divided by V is equal to sigma x plus sigma y plus sigma z multiplied by 1 minus 2 mu complete divided by capital E. So with this change in volume, if we take this capital V part over here, so change in volume will be original volume multiplied by this part. Okay. So what we can write? Say in case if only stress is acting along a particular axis. So if it is one-dimensional stress system, say, then only sigma will be existing, and other two terms, sigma y, sigma z, for example, if it is 0, then volumetric strain for uniaxial force system, it becomes, now from this part, sigma y, sigma z is 0, so only sigma is existing, so that will give sigma multiplied by 1 minus 2 mu divided by capital E. And what can be written? This sigma divided by capital E is epsilon in that particular direction, that is longitudinal strain, along which that sigma is existing. So that strain multiplied by 1 minus 2 mu gives us volumetric strain in case if uniaxial force system is there, or stress is there along a particular axis on that particular system. So with this discussion we will conclude this lecture, and in next lecture we will go through one more modulus of material, that is called as bulk modulus, and it is denoted by capital K. So we have discussed up till now Young's modulus, capital E, the shear modulus or modulus of rigidity, capital G, and next lecture we will discuss about bulk modulus, capital K, and what is the relation between all these three moduli we will discuss in the next lecture.